So our third speaker in the session is Xiahui Li from St Andrews, who's going to be talking about approximate Bayesian inference. Thank you.
Hello everybody, I'm Xiahui Li from University of St Andrews and guided by Dr. Ben Swallow and Dr. Fergus Chadwick. And I feel really grateful to be here and have the opportunity to share our latest research on the novel approximation inference method for compartmental models in epidemiology using STAN. So to start, I will just revisit the very familiar tools for everybody, the compartmental models in epidemiology, which is quite essential for study how the disease spread. And consider the simplest SIR model. As we all know, it has 3 compartments, and the flows between the compartments can be described using a series of ordinary differential equations. And to better reflect the complexity of the real-world data, we can add more compartments and more complicated flows between them to capture more details, such as variable infectiousness, multiple routes of transmission, and also the age-specific transmission. However, the more complex the data, the greater the challenge in estimating the parameters. This is where computational Bayesian methods come into play, which provide a robust tools for tackle this challenge effectively. So under the Bayesian framework, we can derive the posterior distribution by integrating the prior knowledge of the parameters and likelihood. However, for complex models, the likelihood function is intractable sometimes because of the computational prohibitive or analytical impossible. This leads us to use the likelihood frame method. This kind of method circumvents the direct computation of the likelihood by identifying parameter value that produce the simulated data closely resembling the observed data. And the 2 popular examples are approximate Bayesian competition method, we also call it ABC, and also the Bayesian synthetic likelihood method. I believe you have heard these 2 terms multiple times these days and wondering how it works. I'm going to talk about them in great detail. So for standard rejection ABC method, if we want to implement it, we need to specify a few inputs, including observed data, prior distribution, and our selection of tolerance, distance, and summary statistics. And these elements are then integrated into our ABC workflow. So first, we sample the parameters from the prior distribution. We simulate the data from the model given parameters. And we summarize the observed data and synthetic data with a set of chosen summary statistics. And we accept the parameter value if the distance between the summary statistics of observed and simulated data is close enough and less than equal to our predefined tolerance level. Otherwise, we reject it. We repeat the process until the desired number of posterior samples is obtained. Implementing this method will give us a joint distribution of parameter vector and summary statistics, incorporating our selection of distance, summary statistics, and tolerance. By integrating the joint distribution over the synthetic data, we will derive the ABC posterior distribution and use it as an approximation to the true posterior distribution. And we can see from here, the accuracy of approximation is actually jointly determined by our selection of distance, summary statistics, and tolerance. Over the years, many scholars have been working on improving the computational efficiency and approximation quality of the standard ABC method from these 3 aspects. The choice of summary statistics often made empirically crucially affect the performance of ABC. And our work will focus on the summary statistics selection method, which could be classified into 3 categories: subset selection, projection, and auxiliary likelihood. Each of this method has its own advantage, with the subset selection method prized for its interpretability. So for this kind of method, it involves selecting a candidate set of data features and attempting to identify the low-dimensional, highly informative subset. For example, the loss minimization method, which is a 2-stage sequential search algorithm, uses this method to select best summary statistics by minimizing the entropy first and then optimize the ABC performance on a similar data set by minimizing the loose averages. And this method is later on used in our simulation study. Now let's move on to talk about the Bayesian synthetic likelihood method, which is introduced by Simon-Wood in 2010. So in this method, the synthetic data is generated from the model and condensed to summary statistics, and we assume the summary statistics follow a multivariate normal distribution. By simulation, we can estimate the parameters mu and covariance matrix, facilitating the construction of a synthetic likelihood for evaluating the model fit. And also the likelihood can be explored using the MCMC sampling. So inspired by this work, there's a few of questions we would like to ask. One is, how can the summary statistics be selected to be informatively representative? And are there more efficient ways for exploring the likelihood? Therefore, we proposed a novel Bayesian inference scheme incorporates the Bayesian synthetic likelihood framework, facilitating inference in models with intractable likelihood. By implementing ABC subset selection method in the data to statistic transformation stage, we identify the best subset of summary statistics, which is low dimensional and highly informative for constructing synthetic likelihood. And the resulting synthetic likelihood will be used for posterior sampling for improve the computational efficiency and also the inferential precision. And to date, our simulation has included random walk metropolis Hastings algorithm and also the Hamiltonian Monte Carlo algorithms in STAN. And due to their performance, so we will mainly share the result we have for implementing HMC in STAN, because it just built effectively on our methodological framework. So what is Hamiltonian Monte Carlo? This method stands out by using physical principles to navigate the high-dimensional probability distribution effectively. So it combines the position and momentum, where we can see the parameter value and auxiliary variables that propel the sampling process across the probability landscape. And the key to the success of HMC is the leapfrog integrator. It simulates the trajectories that conserve energy, we can see from the plot, and allow for significant jumps across the parameter space, and also avoid the inefficiencies of random walk and result in high acceptance rate for new samples that we're going to see for the illustration in the simulation part. And what is STAN? STAN is a platform for statistical modeling and high-performance statistical computation. And it automates much of this process and allows users to define their models in a probabilistic programming language and handle the complexity of HMC behind the scenes. So in our simulation study, we used the deterministic SEIR model for depict the epidemic dynamics. And our aim was to estimate the parameters of SEIR model using the proposed method with HMC sampling in STAN, based on the summary statistics suggested by ABC loose minimization method. The data we're using is the daily count of individuals from different compartments, simulated from the deterministic SEIR model with the arbitrary choice of parameter values. And we set the initial condition for the epidemic to start, and the simulation lasts for 100 days. Through exploratory analysis, we identified a candidate set of data features and trying to find the lower dimensional subset through loose minimization method. And this process has suggesting that the average exposed and infected population over time, and also the final size of recovered population can build up a basis for us to construct the synthetic likelihood. In the posterior sampling stage, we specify a Bayesian model in STAN incorporating the uniform prior of the parameter of the parameter values and also the synthetic data based on the summary statistics. The model fitting process is conducted using HMC to derive the posterior samples. We executed 10,000 iterations and treated the first half as burn-in. So the trace plot for the parameter has shown a good mixing behavior, indicating good overlap and suggesting convergence. The acceptance rate exhibits high densities near 1, indicating efficient sampling and well-tuned proposal distribution. And the total computation time for 4 chains collectively is about 11 minutes. Highlights the computation intensity of this whole process. And the contrast between the broad prior distribution and the narrow posterior distribution has demonstrated that the data is highly informative and leading to precise parameter estimates. As evidenced in the posterior summaries, the mean of the posterior sample is closely aligned with our true value of the parameters. So in conclusion, our method combines the strength of ABC and MCMC to enhance Bayesian inference in compartmental models. It allows ABC to reduce the dimensionality by pinpointing the most informative summary statistics, while MCMC provides a framework for reliable and accurate sampling, posterior sampling using synthetic likelihood. And we recognize that this method demands significant computational resources, especially with high-dimensional models, and the outcomes might vary with different sets of summary statistics and priors. So going forward, we will explore alternative summary statistics and priors for improving the accuracy and robustness. We also will delve deeper into the theoretical underpinning of the method and trying to extend its application to more complex models with vital dynamics for broader scenarios, and also use the real-world data to validate our method. And in the end, we will be very happy to hear your thoughts about this method and have more conversation with the interested parties. Here are the references for our work. Thank you very much.
Any questions?
I have one. Thank you for the nice talk. Have you considered other distributions instead of the normal for the kind of to approximate the likelihood of the summary statistics? Like in the synthetic likelihood, you assume that the distribution of the summary stats come from normal. Have you tried other distributions?
So from Simon's idea, the reason why to follow a multivariate normal distribution is for mathematical convenience and computational convenience. So we adopted this model, this method, and haven't tried any alternative assumptions yet. But we will do that later. Thank you.
Yeah, go ahead.
Yeah, thank you very much. That was really nice. And I'm going to ask a question which might be a stupid question, so please. But it's a question that I've often thought about, but never been brave enough to ask before. Is it at all sensible or likely or possible that actually different methods of fitting, so all the different kind of ways of inference, that the different parameters are actually best fitted by different approaches? So the parameters that we have in these models are often have very different positions within the modeling. Yeah, and we end up with having different sensitivities of the model outcomes. And yet everyone fits all the parameters with the same methodology. But I wondered if there was anyone doing anything about thinking, so the way that you have implemented the ABC and the synthetic likelihood, is that best suited to one parameter or another? And would it be possible to integrate that method with another method if two parameters were actually better fitted by different approaches?
Thank you for your question. It's definitely not stupid. It's quite hard for me. Yeah, I think it's a very good thought about having more tailoring on the method to fit the parameter value more precisely. What I could think about is doing some preliminary study about setting the prior distribution like more detailed according to different parameters. For example, for transmission rate, for incubation rate, they'll have different performance, so we can have different prior distribution for that. But yeah, we will later on think about having more detailed method to fit in the different parameter values. Thank you.
Okay, let's thank Xiahui again.